location, or the 0 location, or s minus z. You go, wait a minute, it's usually a plus. Why is it usually a plus, not a minus? Why is it usually a plus and not a minus?
Because it carries over from.
Yeah, because usually these poles and zeros on the left half plane. That's where we're used to seeing them. But anyway, we can do that. So, in order for s minus p to be a negative number, what does s have to be? Smaller than, i.e. to the left of p, or to the right of p?
Right.
Smaller than. If it's smaller than p, then it's to the left of p, the pole, and then it's a negative number. Then this overall is negative. Same for the zeros. But in order for the overall transfer function to be negative, which it must be, in order for what to work out? The denominator of the closed loop transfer function, which is equal to something, we don't know what it is on top, 1 plus k times g of s. So why does this have to be negative? To get a pole of the closed loop transfer function. Because k times that negative number has to be negative 1. Right? So, this has to be negative to work. That means the real axis rule tells us that for the left of an odd number of poles and zeros on the real axis, then we'll have some root locus. We don't know which way it's going or where it started from or where it's going to. So let's take a look at this. What do we got? We have a 0 at negative 6. So what you're doing on your paper is you're following along and doing the same thing. So that when you're done, you have a set of examples. We have a pole at negative 1. We have a pole at negative 10. So first thing that we apply is the real axis rule. Is there a root locus here? Are we left of an odd number of poles and zeros?
No.
Is there a root locus between here and here?
Yes.
Okay, there is root locus between here and here. Is there a root locus between here and here? Is there a root locus here?
Yes.
Okay. Now, if we know that our root locus lines start at closed open loop poles and end at open loop zeros, is this all we need for this section?
Yeah.
So it's just doing this. Here, how many excess poles do we have? That is, how many more poles do we have than we have zeros? One more. So there is going to be one root locus line that goes to infinity. If there's only one root locus line that goes to infinity, where does it go to infinity?
Negative infinity.
Okay. Yeah. Are we done? We know we're going to put a little arrow on this to say it starts here and goes out to infinity. Okay, what can you draw from those conclusions? Can you draw from this root locus plot?
We are very stable.
We have a very stable system. We can do what with the gain? Will it ever go unstable? Okay, something about that statement should bother you. Yes?
Well, my question was, how can you know that you could increase the gain without messing with this?
Because the closed loop poles, this closed loop pole, the one that's slowing the open loop pole here, but the closed loop pole that's represented by this line as k gets bigger, that closed loop pole simply becomes a faster and faster exponential result with eventually a smaller and smaller coefficient in front of it. This one over here just gets faster and faster and faster. So the result just keeps getting faster and faster and faster in the closed loop for an increased gain. So it never moves into the right half plane, so the system never goes unstable. If none of the root locus lines move into the right half plane, it'll never go unstable. Now, we'll come back to this again and say, yeah, that sounds nice, but is it really true? And that's where we have to consider things that we don't normally consider. Okay, so that's the first one. Eraser. Eraser man. Right? Oh, darn. Doesn't really matter in this case, but I can now show you that if you actually figure out the root locus, what do you get? Exactly that response. All right. So we have a new transfer function here. Do we have any zeros?
No.
Do we have any poles?
Yes.
Where are those poles?
-2.
So that's an open loop pole. That's where one of our root locus lines is going to start. There's another open loop pole right here. That's where another one of our root locus lines are going to start. Okay, what's going to happen? First, real axis rule. Is there a root locus line here?
No.
No. Yes.
Yes. So there's root locus line here. That does not mean it starts and ends the way I'm drawing it. Just that there is root locus there. Okay, is there any over here? No. So the next step, there is a branch that starts at each one of these open loop poles. So it's going to go in this direction. Where are they going to collide?
Somewhere.
Yeah, somewhere. Our first guess is in the center. Where's the center?
-6.
Okay. Now they have to go somewhere. Where are they going to go? Pardon? Yeah, in some direction.
We're critically damped.
Yeah, they're now critically damped. If you turned up the gain high enough that the two poles meet at -6, and that is actually not a pole, it's not an X, that's my two arrows. That's really badly drawn. There, my two arrows come together right there, my two root locus lines come together right there, and then what happens to them? We can't overlap. So they have to go to infinity, so what do they have to do? They have to leave the real axis. So some people ask, well, which one goes up and which one goes down? But it doesn't really matter. They go up and down. Okay. So how do we now figure out? They're going to do this. So these root locus lines, they're going to collide there. Or somewhere. We're not exactly certain where they collide. But our first guess is in the center. And then they go this way. Now, they will always leave at a right angle. Unless they're leaving directly from poles, or in which case it has to be more than two poles for them not to leave at a right angle. Pretty weird. We'll get to that later. They always leave straight up and straight in. All right, next question. We need to figure out where they're going. Nephi has already said they're going to infinity. But how many more poles are there than there are zeros?
2.
Well, the number of zeros is equal to 0. Not 6, 0. The number of poles is equal to 2. So n minus m is equal to 2. So how many lines have to go to infinity? 2. Yeah, 2 lines go to infinity. So you look at the little chart on your root locus notes, and which way do they have to go? Or, you remember the kind of rule, 360 degrees has to be divided into two pieces. So they go, well, how many degrees apart are these two lines? 180. That means they either go this way, or that way and that way. That violates real axis rules, so what must they do? Straight up and down. How come they can't go this way again? Yeah, they're not complex conjugates of one another. So they go straight up and down. Okay, next thing is we have to find the center point from where they leave. Yes?
Isn't it also that there's no zeros to affect the behavior of those lines going off into the X?
Yeah, no. The asymptotes will be straight up and down, period. And the asymptotes will leave from this centroid point I'm about to figure out. Now, because there are no zeros, the actual lines will follow the asymptotes exactly right from the start. But the asymptotes are going up and down, period, no matter what. This, if there was a 0 or other poles, then it may curve into that. But in this case, it's going to be very simple. So we add up the poles. Where are the poles? -2 plus, where's the next pole? -10. And we subtract off the zeros. Are there any zeros to subtract off? Nope. And divide by that number right there, n minus m, which in this case is 2. So -2 plus a -10 is -12. -12 divided by 2 is -6. So there's my centroid right there. My sigma. And there are going to be two asymptotes that go straight up and down. What do you think those two locus lines are going to do? Exactly follow those, right? Now, we really don't know that for sure at this point. We're assuming this, but it could break away from here. That's what's called the breakaway point, where these two come together, in which case it might have to do something like this. But because there are no other poles and zeros, and because it's just two, I think it's going to do the very simplest thing that it can do. So let's check and see what it does. Sure enough, dead. Okay, questions about that? Are we starting to learn the rules a little bit?
I have a question.
Yes.
Will you ever get more than one centroid?
No. No. There will never be more than one centroid. Because we're adding up all the poles, we're subtracting off all the zeros and dividing by n minus m. There's no other way to do it, so we don't ever end up with more than one. Now, having said that, there are times when it very much looks like there's more than one. And that is if you have a cluster of poles and zeros close to the origin, and then you have maybe some more poles way out here, then you could kind of figure out a local centroid for this to see how things are going to look locally. And then you might take into the others to see what really goes on. So there are times when figuring them out separately does sort of make sense. So that wasn't clear, and it won't be for a while. So a real centroid, there's only one. And the way we figure things out, we only ever figure out. Okay, let's go down. All right, another one. Do I have enough space here? I need more. I need to be able to reach this, is what it comes down to. Maybe if I did one more, it'd be right on the line. Look at
Right
that.
on the line.
All right. My x-axis, or my real axis, is right on that joint. Okay. Anybody recognize this particular transfer function? That open loop transfer function? Very first lab? I don't think we really spent a lot of time looking at it, but that is actually the transfer function, as best I can figure out, for the crude servo that we used in the very, very first lab. Now, we just looked at one of these where it went straight up and straight down. So as the gain got bigger and bigger and bigger, this one that was coming in from the right was moving faster and faster. So its time domain expression was faster and faster because that pole was coming in. And we got a critically damped case. And it did something like this. And where was probably the very best place to put our poles? So I'm looking back at the one that we just had on the board. Maybe I should do this. Oops. I don't want to show you that yet. So, should we use a very small gain? Or would a bigger gain be better? Is this better? Yeah, because the one on my right hand here, that's representing the slowest of the two exponentials, and it's getting faster and faster, right? Faster and faster. Is this gain the best of all? Absolutely zero overshoot. That's the place I want to put it. If I can tolerate better overshoot and I want more speed, is this better?
Yeah.
Is this better?
Yes.
Yeah.
Okay. This is as best we can go because I can't get any taller.
There's a stick.
But in reality, what's the best you probably can do if you can tolerate 4% overshoot?
45.
45 degrees. So if this is at -6, we would put it up there, about where that arrow is up there, and about where this arrow is right here. We put the closed loop poles there and there. So we can figure out what the gain is for that. It's a little difficult to figure out what the gain is for that, but we can do that. Okay.
Why is it that the 45-degree angle is the optimal place for it?
It's because it's an easy spot to find. It only results in 4% overshoot, which is often not is acceptable. It's often acceptable. And it is much faster than the critically damped case. So it's kind of this combination of usually it's okay,
It's got a lot of improvement over a critically damped case, and it's easy to find.
Gotcha. So it's kind of just the result of exponentials where your 4% is going to land at 45 degrees.
Yeah. The amount of overshoot that you get, I don't know if I've ever read through that equation very well, but it's like e to the minus b over a pi or something like this. It's an equation you've used in your homework, I know that. And it turns out that if you work that out when a and b are the same, then it's like e to the minus pi or something. And that turns out to be 0.044. So it turns out that it's not a lot of overshoot.
Math. So the math shakes it out that way.
Math shakes out that way. All right, continuing on back to where we were. So now I'm looking at the crude servo that we had in the lab. Hey, right there. What are we going to do? Let's put down, what's the first thing you do? You look at the open loop transfer function, and we do what? So this is interesting. This is a real system you've played with in the lab. You already know kind of how it responds. What happens is you turn the gain up.
It's unstable.
First, it gets faster and faster response. Then eventually, it starts to overshoot. And then eventually it does what? So we know already from that experience in the lab what those closed loop poles must do. One of them must move away from the imaginary axis as we turn up the gain because it gets faster. And eventually we have to have a pair that go away from the real axis and it starts to ring and overshoot. But eventually something must cross over into the right half plane or we wouldn't get what effect?
Instability.
The oscillation. So let's see if our Locus plot tells us the same thing. There is a open loop pole at the origin. Where does that come from, by the way?
The
53, about right there. Why is there an open loop pole at the origin for our DC motor and gears? Because the output of that system was what?
Position.
Position. And if you put in a DC voltage into a DC motor, does the position keep getting bigger and bigger and bigger?
Yeah.
That's exactly what we expect. All right, so if we used an output, if we looked at the output not as position, but as velocity, what happens to that pole at the origin? Disappears. But because this particular transfer function is theta over Vn to the DC motor, that's why it has that pole at the origin. And in fact, that's the only thing that would be different if this were a velocity. Why? Because what's the relationship between velocity and position? Yeah, simple derivative, which is that s. Gets rid of that s. All right, let's go on here, because we would integrate this. No, we differentiate to get velocity. And that would be multiplied by s, which cancels out the s in the denominator. Moving on. What do we expect? Real axis rule tells us
Yes.
all of that. How about this section?
Nope.
Now we're left with 3 of them. So this, there's no other poles or zeros, so it must go out that way. Okay? Looking at the fact that the grid locus lines must start at these 2 poles, what do we think happens? Somewhere in here they have to collide, right? Best guess to start with is right here in the middle. And then they must take off, and they must take off at a right angle. Okay, but what happens now? Now we have to figure out our centroid and our n minus m. What is m? The number of zeros.
0.
What is n? The number of poles.
3.
If you can read that, you can read Polish. 3. So n minus m equals 3. Where's our centroid? By the way, what does that mean? Okay, what does that mean for the asymptotes? How many are there going to be? 3. 360 degrees divided by 3 is 120 degrees apart. So, because of the need for complex conjugate pairs, that could either mean one that way and here, but can that happen because of the real axis rule? In fact, we already know that one goes out that way, so where do the other two go? At what angle off of the x-axis if they're 120 apart?
60.
So 60 makes 120 total. So, but we don't know where they start from. So how do we find that start point? The centroid equals the three poles. 0 plus a negative 16.64 plus a negative 53.78 minus any of the zeros. There are no zeros, so there's nothing to subtract off. What's n minus m? I do not know what that number is.
Negative 23.473.
How is that possible?
Negative 23.473. Oh dear.
Yeah.
The center, there's no root locus there.
They're asymptotes. They're asymptotes. We don't care.
Yeah, we don't care. We don't care. Last time it was right where there was root locus. And the root locus lines immediately took off and followed those centroids. I can't do that now. The centroids here takes off from here. So let's see, this is going to be about 60 degrees. So it's going to be like about this and this. So what I'm trying to draw is about 60 degrees here and 60 degrees there. Like that. So what's going to happen? Well, these two that leave here eventually have to run up and start following these two lines. So they will do this, and they will do this, and they will not go out. They will always get closer and closer to the lines. So what does this root locus plot tell us?
Bad things happen.
Yeah, bad things are going to eventually happen. It tells us, first of all, this pole over here is not going to have much effect on a response. Sort of. Except it's this pole, which means that these are this way, which means it eventually goes into the right half plane, so eventually it has a lot of effect. But initially, these two dominate the response. And the response is going to look like two exponentials, one faster, one slower. And eventually we get to critical damping, right? And then we turn up the gain some more, and we can get to this point. Why is that point significant?
45.
Is it steep? Yeah, that's probably going to give us just a little overshoot and kind of a fast response. But we keep turning the gain up, what's it eventually going to do?
Well,
Yeah, it's eventually going to start to oscillate. Let's see if we're really on target here. Now, notice that my drawing of my curves and my asymptotes were not very accurate. Could I have made them more accurate with a protractor? Could have made my asymptotes more accurate, but otherwise not so much. But do I have the general shape and the general idea of what's going to happen? Yeah. So I could have used a protractor, or otherwise, if I knew that this was at 23 point something, could I have figured out where that line crossed up here by just using some trigonometry at a 60-degree angle? Yeah, I could have done that.
So when the right part related diverge from the real axis, it's not quite to the center, slightly to the right of center. Is that going to be able to be calculated? Or I guess critical damp from just
Okay.
Yeah.
He's saying there's another thing that's different too. It's where this actually leaves from here. Well, pictures don't line up exactly anyway. But where this leaves it here. Because actually, if I move this over just a little bit, it would even, well, anyway. It's not directly in the center of these two. We kind of initially guess about the center because we don't know. But this point right here, which is called the breakaway point, because that's where the two locuses hit and then break away from the real axis, that point can be figured out exactly. It's not necessarily a very easy calculation. But initially, we don't know quite where that is. So we guess about the middle. Questions about this? Now, yes, Benny.